I love taking my child to research conferences with me. But when they were a baby, they would often cry a lot every time the plane would take off or land. It's because their little ears will pop and hurt. It's pretty common. Most people know it has something to do with pressure, but they don't necessarily have the details. Well, this is where we can turn to the ideal gas loss. Esto es Real Chem. The calculation used in the ideal gas loss can seem complex, but the key thing is to always return to the proportional relationship described in each law. Proportional reasoning helps us build and harness our intuition with numbers. Here, we bring that type of intuition to our understanding of gases. Exploremos. Experiments show us that the gas volume goes down as the pressure in a container goes up. We can demonstrate this today by using a large syringe with a small balloon inflated inside. If we block the end of the syringe off, force the plunger in to increase the pressure inside the syringe, the balloon gets smaller. Conversely, if we pull the syringe plunger further out, the pressure inside the syringe decreases, and the balloon gets bigger. Boyle's law is an inversely proportional relationship. If the pressure is doubled, the volume is halved. We can use a weather balloon to help us visualize the application of this gas law as it races through the atmosphere. On the ground, before we launch it, the volume of the balloon is 1.41 times to the 4 liters. The temperature is 21 degrees and the pressure is 745 torr. When it reaches a height of 20 kilometers, way up in the stratosphere, the temperature has dropped to minus 48 degrees, and the pressure has also dropped to 63.1 torr. Our job is to work out what the volume will be when we get there, which is very important for designing a balloon that won't pop at altitude. First, let's think about the pressure change. This is like what happens inside our ears on a flight. While on the ground, the gas in our ears is at the same pressure as the gas in the atmosphere. But as the plane races, the pressure in the air around us drops, and the gas in our ears tries to expand to a larger volume. We feel this as a stretching sensation in our ears. As pressure decreases, the volume of the gas increases. So, volume is inversely proportional to pressure. As the balloon rises, the pressure goes down from 745 torr to 63.1 torr. We can use proportional reasoning to calculate the effect of this on the balloon's volume. Okay, here's the way I like to do this. Because of the proportional relation, I know that I will multiply my initial volume by either 745 torr divided by 63.1 torr, or 63.1 torr divided by 745 torr. My intuition tells me the decreasing pressure will increase the volume of the balloon. So I must be multiplying by a number which is greater than 1, which means we must use our first choice. 1.41 times 10 to the 4 liters multiplied by 745 torr divided by 63.1 torr equals 1.66 times 10 to the 5 liter. The decrease in pressure increased the volume by more than a factor of 10. As the balloon rises, the temperature also drops from 21 degrees to minus 48 degrees. As the temperature decreases, the volume will also decrease. So, volume is directly proportional to temperature. But this proportionality requires that we use temperature in Kelvin. So, our temperature has decreased from 294 Kelvin to 225 Kelvin. So, we're either multiplying by 294 Kelvin divided by 225 Kelvin, or 225 Kelvin divided by 294 Kelvin. Now, our intuition tells us that the volume is decreasing due to the decreasing temperature. So it must be the ratio that is less than 1. This means 1.66 times 10 to the 5 liters multiplied by 225 Kelvin divided by 294 Kelvin, which gives us 1.27 times 10 to the 5 liter. Here, we did this calculation in a stepwise manner, considering first pressure and then temperature. For the change in pressure, we can calculate 1.41 times 10 to the 4 liters multiplied by 745 torr divided by 63.1 torr equals 1.66 times 10 to the 5 liter. For the change in temperature, we get 1.66 times 10 to the 5 liter multiplied by 225 Kelvin divided by 294 Kelvin, which equals 1.27 times 10 to the 5 liters. But we could have done this all at once by stringing all our ratios together. Let's try it. The new volume is equal to 1.41 times 10 to the 4 liters multiplied by 225 Kelvin divided by 294 Kelvin multiplied by 745 torr divided by 63.1 torr, giving us the answer of 1.27 times 10 to the 5 liters for the new volume of the balloon high in the atmosphere. So, next time you sit next to a crying baby on the plane, remind yourself it is just the gas in the ears expanding, just like the hydrogen in the balloon. If they're lucky, their eustachian tube will open and release some gas, relieving the pressure in their ears. If not, while it won't make the discomfort any less, it may just make the time pass faster if you think about the pressure changes that are the cause of their ear pain. Explora y diviértete. So explore and remember to have fun.